Hello everyone. Welcome to the video on fixed capacitor thyristor controlled reactor. I'm Ganesh from Kekewag Institute of Engineering Education and Research, Nashi. Welcome in this video. In today's video, we are going to introduce about the FCTCR scheme, that is fixed capacitor thyristor control scheme. The FCTCR scheme stands for Fixed Capacitor Thyristor Controlled Reactor. This is a type of SVC, that is static VR compensation, used for voltage control and reactive power compensation. What are the key components of this? This consists of a fixed capacitor which provides the leading reactive power. It consists of a thyristor controlled reactor, provides dynamic lagging reactive power, means the power is changing with respect to time, or you can change the power by the firing angle control of the thyristor controlled reactor. What is the working principle of this? The TCR firing angle is controlled to regulate the net reactive power. The net reactive power supplied by the capacitor can become a variable if you control the firing angle of the TCR. And it combines with the fixed capacitor for smooth voltage control. So this is the generalized schematic diagram of FCTCR scheme. Here we have a transmission line. This transmission line is on this side it is connected to the sending end. On this side it is connected to receiving end. On receiving end there is a load. Okay, suppose the load is having the active and reactive power both. So to supply the reactive power, we have designed a capacitor, but we want a variable reactive power, so that we connected one anti-parallel TCR, anti-parallel thyristor with this in series with the reactor to have a TCR combination. So let's see the diagram. So this consists of a fixed capacitor which provides the constant reactive power. It enhances the system voltage stability. It minimizes the transmission loss and work efficiently with TCR for providing the smooth control. On this side, this is a TCR which provides a smooth continuous control. With the firing angle alpha, we can control the current component in the lagging and leading mode. Mainly the ITCR is in lagging, but the current of the IC plus ICTCR may be the lagging or maybe the leading. So it having the fast dynamic response, as we are using the static switches, power electronic switches, that is SCR, hence fast dynamic response. Then reduce the line losses. It improves the power factor. As power factor is improved, the losses are reduced. Enhance the system stability, prevents from over voltages and under voltages. Here we are using the transformer. Transformer allows the safe operation of the thyristor at lower voltages. Maybe transmission line is consist of 400 kilovolt. The SCR may not be available for a 400 kilovolt at that time. With the reduced rating of the SCR and in connection with the step down transformer, we can use this FCTCR of the reduced rating over here. It protects the power electronic from high voltage stresses. The line high voltage stresses will not come into the FCTCR scheme. It improves the efficiency and it helps into the harmonic mitigation. Uh, let's do the analysis of this FCTCR scheme. Let the load connected to the system is P plus JQ VA. So on this side we have connected the load P plus JQ per unit, rather VA it is a per unit. P is the active power in per unit and Q is the reactive power in per unit. I want to maintain the power factor at unity. Okay, so at the load power factor supplied by the source, that is the only active power will be supplied by the source, not the reactive power. Reactive power is totally taken care by this FCTCR scheme. Hence, the reactive power QC must be equal to reactive power of the load, that is V square upon XC. XC is the reactive capacitive reactance of this capacitor. So I want to calculate the susceptance. So susceptance BC is equal to 1 upon XC. XC is equal to 1 upon omega C. So you can write it as J omega C. So QC is equal to Q B square upon XC. That is, you can type it as a BC V square per unit. So that BC is equal to V square upon QC. So BC is the capacitive susceptance. To make the capacitive reactor power variable from 0 to QC, that is whatever the reactive power, we want to make it variable from 0 to QC, then we have to connect the TCR scheme in parallel with the fixed capacitor, such that the firing angle of this TCR will control the current ITCR. Hence the net current supplied is equal to IC plus ITCR. So reactive power rating of the TCR must be equal and opposite to your reactive power supplied by the capacitor. Hence, QL is equal to QC. So let the thyristor consist of the inductor L in series with the anti-parallel thyristor. The firing angle alpha determines the effective reactance or effective susceptance. The effective susceptance, maximum effective susceptance is V square upon QL. But due to the thyristor control, we will get the variable susceptance of the TCR. So BTCR, which is the function of alpha, is equal to BTCR maximum, which is determined from this formula, pi minus 2 alpha plus sine 2 alpha upon pi. So by this formula, we can determine the susceptance offered by the TCR at the firing angle alpha. Now, let us consider that when thyristors are fully conducting, that is alpha is equal to 90 degree. If we keep the alpha is equal to 90 degree, the total maximum current is flowing. ITCR will be the maximum. ITCR will be equal to IC, hence QL is equal to QC. When the thyristor is fully blocked, that is alpha is equal to 180 degree, means no firing angle is given, alpha is equal to 80 degree, so that this will act like open circuit. Hence the total current supplied by the SVC is equal to IC, hence total current is the capacitive in nature. In intermediate range, when alpha is lies between 90 degree to 180 degree, it provides the variable it provides the variable susceptance. So we will see the formula of variable susceptance in the next slide. Hence the total reactive power supplied by the SVC is equal to QC minus QL, where QL is the function of firing angle alpha. Now, let us study the VI characteristics of FCTCR. In this VI characteristics of FCTCR, if you observe, ISVC is taken on this axis, VSVC is taken on this axis. This is the BL max line. So this entire area which is shown here, it is controlled by the TCR, whereas this line, fixed capacitor will work only on this line, not on this area. Fixed capacitor is having this line BC line, which this current is equal to IC max current. When you connect FC and TCR in parallel, this entire shaded range is the operating area for the FC-TCR scheme. In the FC-TCR operates as a shunt compensator, provide both capacitive and inductive power. The characteristics is non-linear due to the because we are having the firing angle control, so hence the characteristics is non-linear. It consists of two distinct operations. Capacitive region, that is positive VAR generation, that is leading power factor. Inductive region, negative VAR generation, lagging power factor. Capacitive region, in capacitive region, the operating point will be on this side. The capacitive region FC is a dominant, and it is having when there is a low load condition. When the system voltage is low, a fixed capacitor injects the reactive power and improving the voltage stability. When system operates in a capacitive region, it means that it supplies the reactive power to the grid. At this stage, TCR is fully blocked. Then in inductive region, TCR is a dominant in high load condition. When system voltage rises, excess capacitive compensation can to lead over voltages. The TCR is triggered by the adjusting the firing angle alpha. It allows to absorb the inductive reactive power. The system moves into the inductive region, means the system operating point will be in this region. Hence net effective power is reactive power absorption. In control transition between the region, the transition between the capacitor and inductive is smooth depending upon the TCR operation. The net reactive power Q net is equal to QC minus QL, and QL is the variable which is the function of firing angle alpha, which can be varied from smooth full capacitive state to an inductive state. So in a three-phase system, how this FCTCR scheme is connected? In three-phase system, the fixed capacitors are connected in delta, and TCR schemes are also connected in delta. Here multiple TCR scheme is connected. On this side, there is a load. Depending upon the controller action, the TCRs and TSC, the TCRs can be turned on here. The source is from this paper, which is indicated in the red color below. What are the advantages? The advantages of FCTC scheme is smooth and continuous reactive power control. So, unlike the FCTSR scheme, that is thyristor switched reactor, thyristor switched reactor provides us in steps reactive power. But FCTCR is having the smooth control over the reactive power by adjusting the firing angle. Voltage stability improvement, dynamic voltage can be adjusted under over voltages, and under voltages can be handled by the this TCR. Hence FCTCR scheme having the highest voltage stability. Power factor correction, it can provide the leading power factor to lagging power factor correction very smoothly. Hence, unity power factor can be achieved. Fast response time, it is having the quick response as compared to the mechanical switching. Then reduction in transmission loss as reactive power flow is reduced through the line. The reactive current is reduced through the line. Hence, the losses in the transmission lines are reduced. I square R losses are reduced. Hence, the efficiency of the transmission line increases. Increase the system stability. It increase the transient stability area. Hence, the transient stability enhancement is there. In especially in case of weak grid, it provides the compensation against the reactive power fluctuation. It is cost effective as compared to StatCom. The StatCom is a very costly that as compared to the FCTCR scheme. But there are some disadvantages also. Disadvantages is generation of harmonics. When thyristors are partially conducting, at that time in a single phase FCTCR the third harmonics is the dominant, and in three phase FCTCR scheme the fifth and seventh harmonics are the dominant, and the highest harmonic generation is observed in the FCTCR scheme. Higher switching losses as due to the switching of the thyristor, it is observed that the switching losses are greater, hence overall efficiency may get reduced. Fixed capacitor can cause the overcompensation. Sometimes if the fixed capacitor also can cause the overcompensation and causes the over voltages issue if the firing angles are not properly generated. Limited control over the transient condition. StatCom can handle the transient condition better way as compared to the FCTCR scheme. A bulky equipment and space requirement, a large size of inductor and a transformer, a physical size of these pack devices is bulky. And the last one is the require additional harmonic filter. To suppress the harmonics, we require additional filter, passive filter across the FCTCR scheme to absorb the harmonics generated. Then there is one solution to handle the harmonics. Instead of connecting one single TCR, connect the multiple TCR, and it is switched type. Instead of giving the firing angle varying from alpha to 180 degree, it is switched on or off at, that is alpha is equal to exactly 90 degree or exactly 180 degree. At that time TCR is also known as the TSR, that is thyristor switched capacitor. In this diagram if you observe, transmission line, then step down transformer, one fixed capacitor and three TCRs are connected here. So three TCR is having the susceptance BL1, BL2 and BL3. So this BL1, BL2 and BL3 here you can observe. So let me mark this BL1, BL1, BL2 and BL3. Let us assume that all three TCRs are identical. This is the TCR1, this is the TCR2 and this is the TCR3. All three TCRs are identical in nature. Okay. So I'm assuming that all TCRs are identical in nature. Okay, let me erase this. Okay. Now so susceptance offered by this scheme with transformer, assume that all TCRs are identical. So if we make an equivalent diagram of this, susceptance of this is equal to B sigma. Susceptance of this is equal to BC. Sorry, by mistakenly B is printed here. It is a BC. It is BL1, BL2 and BL3. That is the reactance. These are the variable type of the reactor. Then BSBC offered. If we observe here, the BC, BL1 and BL2, BL3, they are in parallel. So in parallel, susceptance are added. That is net susceptance offered by this FCTCR is equal to BC plus BL plus BL2 plus BL3. But it is in series with the B sigma. Hence, that is transformer susceptance is in series with this scheme. So in a series connection, we have to apply the formula of parallel resistance. So B sigma multiplied by BC plus 3BL, because these three are identical, so it is a 3BL. BC plus BL1 plus BL2 plus BL3, but BL1, BL2, BL3 are equal. Hence it is BC plus 3BL. divided by B sigma plus 3 plus BC plus 3BL. Here I am using the 3 TCR, hence it is multiplied by 3. If you are using the 4 TCR, then it is 4. If it is N TCR, then you can multiply instead of 3, if we multiply with the N BL. So this is our transmission line. In this transmission line, uh, this is net equivalent diagram. Maximum reactive power absorbed. When the maximum reactive power will be absorbed, when this BL is equal to 0. When this, sorry, BC is equal to 0. At the BC is equal to 0, the susceptance offered by the SVC is equal to SVC minimum. Hence, SVC minimum, you in this formula, in this previous formula, if you substitute BC is equal to 0, you will get the maximum absorption limit by the SCR. So BSBC minimum is equal to B sigma plus into 3BL upon B sigma plus 3BL. So BC is equal to 0 in this case. The maximum reactive power absorption limit is achieved by when BL is equal to 0. Maximum reactive power supplied, that is production, by this capacitor is when this all BL is acting like open circuit, that is BL is equal to 0. Hence BSBC is equal to BSBC max, and BSBC max is given by B sigma BC upon B sigma plus BC. Hence BSBC can be varied between minimum and maximum range. This is the minimum range and this is the maximum range. So let us do through this one numerical. SVC with the fixed capacitor and 3 TCR units along with the step down transformer are used to control the reactive power of the transmission line. So what is given in this problem? So one SVC scheme having the one fixed capacitor and 3 identical TCR unit connected in series with the step down transformer is given. The susceptance of transformer is 4 per unit. Susceptance of this, that is B sigma of the transformer, is 4 per unit. The capacitive susceptance offered by the SVC is 1 per unit. So maximum capacitive susceptance offered is 1 per unit, and inductive susceptance offered is 0.4 unit by this, 0.45 per unit by this unit, and the voltage of the line is 1 per unit. Calculate rating of FC and individual TCR. Susceptance offered and current taken by the SVC if 2 TCR are on and FC is on, and susceptance offered and current taken by SVC if 1 TCR is on. So what is the given data? B sigma transformer susceptance is 4 pu. Why I am taking the minus 4? Because it is the inductive in nature. Inductive susceptance always in minus side, so it is a minus 4 pu. BSBC maximum is maximum susceptance is capacitive in nature, so it is plus 1 per unit, and BSBC minimum is minimum SVC susceptance, that is inductive, hence it is, as it is inductive, it is minus 0.45 per unit. The maximum reactive power absorption limit is achieved when BC is equal to 0. So BSV minimum is equal to B sigma into 3BL. Why I am taking the 3BL? Because there are 3 TCR connected here. So the B sigma into 3BL upon B sigma plus 3BL. If you substitute the value of BSVC minimum as a 0.45 and B sigma is equal to 4 minus 4, you will get this equation. After solving this equation, BL is minus 0.169. It is observed that the rating of the susceptive ratings of the individual TCR is minus 0.169 per unit. Similarly, the maximum reactive power absorption limit is achieved when BL is equal to 0. Hence, SVC is equal to SVC max. So SVC max is equal to B sigma into BC, as a BL is equal to 0. It is B sigma plus BC. So B sigma is minus 4 and BSVC max is given as a 1 per unit. So if we solve this equation, what is the value of BC? BC is equal to 0.8 per unit. Hence the susceptance, now we have to calculate the susceptance offered and current taken by SVC if 2 TCR are on and FC are on. So what is given in this diagram? 2 TCR are on, means this TCR is not working. Only 2 TCR are on and the fixed capacitor is in circuit. So at that time, what will be the BSVC? BSVC is equal to B sigma plus into BC into 2BL. Why 2BL is taken? Because 2 TCR are on. Hence B2L in denominator also B sigma plus BC plus 2BL. If we substitute the values of BL and BC, which we have calculated in the previous first step, so you will get minus 4.8 plus 2 into minus 0.169. So by substituting this value, we'll get BSVC is equal to 0.5223. As it is a positive, means it is a capacitive susceptance offered by 0.223 per unit. I want to calculate the current. The current supplied by ISVC is equal to minus BSVC into V. So that is minus J BSVC into C. So this is obviously J. So J.5223 into 1 per unit voltage is given in the problem, 1 per unit. If it is a 1.1, multiplied with 1.1. If it is a 0.9, multiplied with 0.9. Okay, so it gives the ISVC is equal to minus J.5223 per unit. So minus J indicates that it is the capacitive type of the current. Susceptance offered by the susceptance offered and current taken by SVC if 1 TCR is on and 1 TCR FC condition is not given, means FC is off. So that's why in this problem the BC is equal to 0. Substituting the BC is equal to 0 and 2 TCRs are on. So in this problem it is 1 TCR given. Here I have taken the 2 TCR. Please consider this as a 2 TCR. When 2 TCRs are on, susceptance offered and current taken by the SVC, if 2 TCR instead of 1, 2 TCR is on, then maximum SVC is the minus 0.3117. So what is the minus is indicate? Minus is indicate that it is the inductive in nature. Hence the current is minus J BSVC into 1. So it gives you J.3317 per unit. So hope you understand this numerical. Only one correction is here. Instead of 1 TCR, take it as a 2 TCR in this problem. Okay. Hope you understand the FCTCR scheme. If you like my video, kindly share with your friends. Thank you, and give the likes to my video. Thank you.